Good morning, everybody. Welcome to Machine Vision class presentations, everyone. Today we will have 5 more presentations. I'm really looking forward to those. We have sign language alphabet interpreter, Sudoku-View, bowling assistant, golf swing mastery, and blackjack helper. Quite a sports-themed projects today. That should be fun. Anyway, just a quick note for everyone who's presenting. Whoever presents, make sure to share your screen with audio so we can hear any sound in the video playing. Start off with your project title, and every group member introduces themselves, and then try to show the demo video first off, followed by your slide presentation. And I would like every member to talk about the portion they did in the project as they present. And we'll reserve 15 minutes for this whole demo and presentation, and reserve 5 minutes for question answer from your fellow students and any guests. So before we start, if any of the guests who are joining our class session, please go ahead and introduce yourselves so students know who's here. And you're welcome to ask questions also.
Hello again. I was here on Tuesday, so I'm glad to be back again for the Thursday presentations. I'm Deborah Kiefer. I work for the School of Engineering and Computer Science as the project manager for the Augmented Reality Center.
Thank you, Deborah. Professor Ming is there.
Yeah, hello, good morning. My name is Hua Ming. I'm interim chair of the CSE department. We have been long looking forward to this great class taught by Dr. Mirza. Actually, looking at these projects and the achievements, I'm really proud of all of you. I look forward to looking at some of the details, and definitely wish this demo round great success. Thanks.
Thank you very much, Dr. Ming. I'm glad you are able to join. We have more guests here. You want to introduce yourselves?
Yeah, hello, Matthew Bellafair. I'm a former student at OU. I was here on Tuesday. I work in autonomous vehicles at Pratt Miller Engineering. I look forward to seeing your presentations.
Thank you for joining, Matthew. And we have Israel also here from ABB. Would you like to introduce yourself too? Yeah, he may be getting his coffee. It's very early. Okay, we will have a chance to introduce our guests again, whoever joins us. So let's go ahead and start the presentation. So we're going to start off with group 7, sign language alphabet interpreter. Go ahead, group 7, take it away.
Can you see my screen?
We can.
Okay. Good morning, everyone. We did the sign language alphabet interpreter. I'm Lianne Badawi.
I'm Marrocco.
And I'm Rafi. Okay, so a little introduction to our project. So the first question that we got to ask ourselves is, what if there was a better way to communicate with people who are deaf instead of having a translator? Or what if there was a way to check your sign language without having like a teacher present? There are approximately around 466 million people that are deaf in this world. Um, and their main form of communication is obviously sign language. Not everyone knows sign language nowadays, but that's why we created this machine vision application, so it could allow you to understand someone who is trying to communicate with you through sign language. You could also use this application to learn the sign language alphabet, which allows obviously somebody to communicate through practice and by using this application instead of having a translator with you. Since American Sign Language has different signs for most words and phrases, learning it is it's basically like learning a brand new language. Yeah, you're basically just interpreting the individual letters of the alphabet, but it's obviously something that makes communicating a lot easier.
So a little project overview. Our project aims to use a machine vision application to first detect a hand from a live video. So through this, we use MediaPipe, which we'll go into on the next slide, but basically it detects 21 different key points on your hand. You can kind of see a little bit over here. These are the different key points that it detects. And then we have a little region of interest around the hand. So we just wanted to single it out so that we could extract the X and Y data. Like I said, we'll go into it on the next slide. And then we had to create a model for training. Again, we'll go over this in the next couple of slides, but basically we had to train multiple images to create a model that could recognize what sign language alphabet letter we're trying to display. So then when we have the model, we can compare it to whatever is displayed through the webcam. And then finally, it can display the predicted letter in sign language.
Okay, so basically getting into how this hand recognition basically works. As you guys heard Lianne talk about MediaPipe, what MediaPipe basically is, it's a framework designed by Google. It has built-in software detection to detect 21 different key points on our hands through the joints that we have on our hands.
Rafi, your voice has been Rafi, your voice is kind of breaking up. Maybe you can turn your speaker down. There may be an echo going on.
Is it better now?
No, it's still. Can everybody else hear it properly? Or okay,
I'm hearing static.
Yeah.
Maybe mute your speaker while you're talking. There might be a feedback issue. Don't mute your mic. We can't hear you. Try it again.
Can you guys hear me?
Yeah, we can hear you now.
Okay, perfect. Sorry about that.
No problem. Go ahead.
Okay, so where was I? Yeah, okay, so basically this MediaPipe, it allows you to recognize 21 different key points on your hands, which are led through the joints of your hand. As you guys can see in that little picture that we have, all the red dots are basically the key points that it detects. And as you guys can see, it's basically an out shape of your actual hand. The way this works is This framework inputs a still image, or it could be also a live video, and that's what detects the presence of the hands, and the output basically landmarks. Each key point has its own X, Y, and Z coordinates. The Z coordinates estimate the distance from the hand to the camera when you're actually recording it. This framework also allows you to draw the key points onto the image or along the video. And with Google, for example, when they created MediaPipe, they used over 30,000 different images to train the hand recognition software.
I'm going to talk a bit about how we extracted the data. We used 150 different pictures for each of the 12 letters in the sign language alphabet that we chose to use. So that comes out to about 1,800 pictures in total. But instead of taking the pictures on our own and uploading them to Python, being able to do that, we actually created a separate cell in our notebook that allowed us to take the pictures directly from our webcam. And the way that we did it is we would hold up the sign language letter that we were trying to use. So for instance, this is A, and then I could push the corresponding letter A on my keyboard. And then it would tell me like ASLA number 1 captured, so we could keep track of how many pictures we took. So this program tracks how many pictures we've taken, and it saves them into a subdirectory for each letter, which we then compiled into a larger main directory folder we labeled sign language letters. Looping through the subdirectory inside of our sign language folder, the images were converted from BGR to RGB. That way MediaPipe's hand landmark detection could be applied. We created a temporary list for the X and Y coordinates for intermediate data that we use to normalize those X and Y coordinates. We then applied MediaPipe, and our code checked to make sure that exactly one hand was detected in our training pictures. And it then looped through each hand landmark in each individual image and extracted the X and Y data, normalizing them, and then appended them into a single data list corresponding to the proper letter. If insufficient data was extracted from the image, we then put it into a temporary array, and we didn't use that data. We then saved this to a pickle file to use for our training program, which we'll talk about on the next slide.
So like Mia mentioned, these 3 images up here are just a little sample of the images that we took for each sign letter. This is the letter M. So to train our sign language model, we had to implement scikit-learn. So this is kind of like a neural network where all of our data went. So we created a data dictionary from our pickle file, and then we used all that data to train the model so that it could recognize sign language letters. So we split our data into 2 separate sets. We had one for training and one for testing. 80% of it was for training, and then 20% of it was for testing the program. We also implemented a function from scikit-learn. It's called random forest classifier. So this basically just helped us choose a random 20% of the data, so that we could make sure that we weren't taking images that were too similar to each other. This obviously helped us ensure that the program was running more smooth and improve the accuracy. Once we trained all the images, we saved the sign language detector model using Pickle, and then we were able to even determine how accurate it was testing the programs. I believe it was about 97% accurate.
I'm going to talk a bit about our results. So as you can see on the screen, this is an example of us spelling out the word honey. So you can see the letters H, O, N, E, and Y. Our final image includes the key points from MediaPipe overlaid on the live video. This wasn't needed to make it work properly, but we wanted to draw them on the live video so you could kind of get a feel of how it works and see the key points, where it's coming from, and how you can tell the difference between the hand positions for each letters. So comparing this key point hand data to our sign language model that we created, we're able to predict the letter being signed. You can see that the predicted letter is displayed on the outside of the region of interest in the color black. only one hand is shown for each letter that we're demonstrating because our program was designed only to apply the model of one hand is visible in the live video frame. It detects both hands through media pipe, so when two hands come in frame, it just stops predicting, but you're still going to see the media pipe data overlaid. It's just not going to predict a sign language letter.
So we ran into a couple of problems. The first one was that MediaPipe wasn't recognizing a hand. So it was either because the images that we were taking, part of the 150 images, were either too blurry or the hand wasn't in the frame. So obviously we couldn't get any data from that image. So we kind of had to troubleshoot. So first we removed all the letters except for one data set, and then we would see if we got an error with, for example, A. If we didn't get an error, we'd move on to the next letter, for example, L. Once we found the error that it was causing based on the data set the pictures we were taking, we just retook all the pictures for that set, and then it was working just fine. The next problem we had, like Mia's mentioned before, was accounting for one or two hands. So when we put two hands in the frame, the whole program was crashing. So we thought of a way to just have it detect sign language for one hand. So when you put two hands in the frame, it'll still show the key points on your hand from MediaPipe, like Rafi mentioned, but it won't predict a sign language letter. If you remove both one hand and just have one hand in the frame, it'll predict the sign language letter and run the program how it should. And then another surprising problem we had was the difference between male and female hand size. So like Rafi mentioned, on MediaPipe, the landmarks are measured from different joints. So when we were training our program with the 150 different pictures, we were using female hands for all those training pictures. And then obviously there's a male in our group. When he tried to run the program, it wasn't predicting the letters very well. So we tried to add his images to the training images of his hand, and that actually improved the predictions. So we just had to make sure the model was trained for both male and female hands.
Okay, and then for future considerations, for this slide, basically, the way we can improve this project or this program is with the amount of time that we had, we only considered 12 different letters. Now, like Mia mentioned, we need about 150 pictures for it to recognize each letter per hand that we have. So that would obviously take a little longer for us to do the whole entire alphabet, but that would be something that you could obviously do if you had a little more time. So the second point that I have is almost every single letter in the alphabet doesn't require motion. Now, there are two letters, which are the letter J and the letter Z, that do require motion. So another thing that we can do is we can train our program, if we had a little more time, to recognize motion letters as well. The third point that I have is the alphabet. Obviously, the alphabet that we use is the American alphabet, the English alphabet pretty much. Obviously, there are other languages and other letters or symbols that we have in the world that we can put into this program as well. We could obviously include that for it to recognize it. Or another thing we could include if we had more time would be for it to recognize individual phrases or words, such as like thank you or hello, or if you're greeting somebody, we could include that as well. And obviously, this just in general, this whole entire point of this program or project that we made is to better communicate with people who are deaf if you don't know sign language. Yeah, I know it's basically all just based off of letters, but knowing letters is better than knowing nothing, in my opinion.
So just a little summary of the entire program. We use the program called MediaPipe for hand landmark detection in this machine vision application. We recorded 21 different key points, and each key point had its own X, Y, and Z coordinates. We took only the X and Y coordinates. and trained it with our 150 different images for all 12 of the letters. This was needed to create our model, essentially to train the program to recognize all the sign language alphabet letters. And then we used scikit-learn to train our model, and it was then applied to a live video to detect the language letters. Thank you guys for your time. We're not taking any questions.
Thank you, Group 7. Great presentation and great demo. Okay, we are open for questions. First, I have to say it's a great project. You guys did great work in the very limited time, 3 to 4 weeks. Come to this point, I have a working project, very useful application. So let's open it up for questions from anyone, and you can unshare your screen now.
I have a question. So when you were testing, once you uploaded all your data, did you test it against like different skin tones, or like if people had rings on, did that make a difference?
So in our testing data, we only had the people in our group to use for our training and testing. However, I don't see skin color or rings being an issue due to, we take our data from MediaPipe. It's not just the image that's training it. So it's using the hand landmarks. And like we mentioned earlier in the presentation, MediaPipe used over 30,000 different images to train its program. So it doesn't really have any issue with detecting different colors, skin or rings or things like that.
Thank you, and great job. I really enjoyed it.
Thank you, Deborah. And I think that was a great question. Training of a machine learning model, the diversity of data is very important so that it can handle different situations. So with the limited time, you guys did very well. I would have to say that. You could try it with gloves also, and different colored gloves. So that will also create some diversity in the data. More questions for this group?
Yeah, I have a slight question. I think the group did a really good job. Congratulations. I noticed that you guys treated all the 5 fingers using the same pattern. For example, the thumb, you treat them, the thumb is the same as your index finger and other fingers because you put like 3 joint, right? Or 4 joints. If you actually look at the thumb, it's a little bit different, right, from other fingers. You don't have that many joints. If you actually change the pattern for the thumb, make it a little bit different from other fingers, will that in fact affect the implementation, the design of the overall project outcome? Thank you.
So all of this landmark detection was done through MediaPipe, which fortunately for us already had this framework set up. But I wouldn't imagine that changing the position of the landmark on the thumb would really have an impact, except for just having to retrain all of the hand's landmark detection model, which would definitely take a long time. We did learn that extracting the data and training our program was actually like the most time-consuming part. Especially the more images we added, the longer it took to compile all of it. Does that answer the question?
Yeah, thank you. Thank you, Mia. Thanks.
Any other questions for the group? So one question I had was that you said that you used you used your own data to train the neural net.
Yeah, we took our own pictures.
Okay. Did you find any existing database with sign language? You know, there are existing databases with, you know, different models. You didn't find any?
I don't think we went that route. I think we wanted to train them so we could, you know, have our own hands, have our own pictures, have our own angles, just for better accuracy, I guess. I don't know if we would have been able to trust other models as opposed to making our own. I don't know if Mia, you want to add on, or Rafi. I think it was better to do our own.
We basically just mainly, our main focus of this was to mainly focus it on our hands, since we're the ones training it, because we wanted to make sure when we do record the video that it works on our hands. But personally, I'm pretty sure there's obviously, just like you said, other databases where it has data for us already, but we wanted to mainly train train it with ours so we can actually be kind of, or feel like that we were involved in this when they actually recognize it's our hands.
Yes.
Another thing with using our own data is it made it easier to troubleshoot. So throughout writing the code, we could print what we were extracting and see where any issues arose, rather than trying to find someone else's data set. And if there was an error, trying to go through their data and figure out where that could have come from.
Okay. No, obviously it all worked very well. You know, we didn't have much chance to go into deep details for AI and machine learning. You guys did very well with a few lectures and picked it up and actually made a working application. There is one thing with when you're training neural nets is the familiarity of the data. So with your own hands, it worked really well for your hands. If somebody else is using, you might run into issues. That's why those diverse databases, if you use those also to train, then it's more chance to pick up anybody signing, it will pick up properly. So yeah, I mean, again, limited time and all that. I think you guys did very well. That's a great proof of concept and an application for what you learned in the class. Good job, group 7.
Thank you.
Hey, excellent. Now we move on to group number 8, and they are going to present Sudoku-View. Take it away. And make sure to unmute your mic before talking. Jason, you're presenting?
Jason's going to present. That's fine. Okay.
You guys can see my screen?
Yes.
Perfect. All right, Brandon, if you want to take it away here.
Oh, okay.
Actually,
click
hold on, let me. I didn't
yeah,
even
you have to put it in
There we go.
slideshow.
We're good now.
Okay, I think we're good. So the name of our project is Sudoku-View, which is a Python Opencv Sudoku puzzle solver. So my name is Brandon.
Recent one.
Emmanuel.
And if you look at the next slide, we can show you our video for the project.
Can you guys hear the sound here?
Are you a senior citizen tired of the endless struggle of solving Sudoku puzzles? Are you looking for a quick and easy way to get the solution?
Yeah, who said that?
Introducing Sudoku-View, a quick and easy way to get the solution to your Sudoku puzzle. Sudoku-View uses state-of-the-art machine vision technology to solve the puzzle with ease.
Well, that's great, but can it solve my Sudoku puzzle?
It sure can. Let me show you Sudoku-View in action. After taking a photo of your Sudoku puzzle here, we can pass it through the custom-made Sudoku-View algorithm. What that entails is first we crop the image and fit it so that the rows and columns line nicely. And then we start to eliminate said rows and columns to just get it digit by digit. And then soon after, we get the thresholding to, again, remove the row and column lines. And then once we do that, we can kind of take the digits and pass them one by one through our custom AI, and then pass it through our Sudoku solver algorithm. And then there you have it, our solution overlaid with our original puzzle. Easy as that.
Wow, that sure is something. Thanks, Sudoku-View.
9 out of 10 programmers would recommend Sudoku-View. In fact, here's one of them now. What are your thoughts on Sudoku-View?
Hey, I'm a programmer that has experience with Sudoku-View. Sudoku-View's cutting-edge problem-solving algorithm can swiftly conquer any challenges and even the most challenging Sudoku problems of our time. It even saved me and my grandpa so much time and effort. Now we can go fishing. Thank you, Sudoku-View.
Right, you're our random programmer. Elevate your Sudoku game with our solver today. Warning, Side effects may include enhanced productivity, increased IQ, and envious looks from family, friends, neighbors, and pets. Sudoku-View is not responsible for built-in AI becoming sentient. Ask your doctor if Sudoku-View is right for you today.
Can you guys see the presentation again?
I think if you press the space bar, it'll go to the next one, right?
Oh, is it still on?
Yes.
I have it on.
So-
Okay. You guys can see it, or?
Maybe click the right arrow.
Yeah.
Oh wait, is it still in the preview? Hold on. Let me
Yes.
just stop the share. Let me reshare here. That's not bad. 1 second. Figure this out. I thought. Ah, there we go. Okay. Let me go back to this. There we go. Okay.
Okay, so the main issue that we had was really in life, it's very thing is with Sudoku puzzles, they're very fun, but they can take a very long time to solve the puzzle. So we had come up with an idea of what if we take a picture of the Sudoku puzzle and have the machine vision program solve it for us. So if you look at the next slide, we can show you some of the proposed solution requirements for the project. We decided why not have Python for the programming language, Opencv for the image filtering of the Sudoku puzzle, and AI recognition for the digit to recognize all the digits on the puzzles. Mainly, we used an online repository for the digit recognizer. So here we can see there are three main parts of the solution, which is the filtering and digit recognizer, the solving algorithm, and the solution construction. Essentially, the first part of the project will break the Sudoku image up into sub-images by digit, passing each digit into the digit recognizer, and putting all those digits together to store as a 9x9 matrix double list. From there, the solving algorithm takes the double list from the digit recognizer and looks at the entire 9x9 matrix and checks if a number can be placed in a specific row, column, or 3x3 box, as the rules of Sudoku state, and essentially recursively solves the puzzle using backtracing and prints the solution to a 9x9 matrix. And from there, the solution is constructed by iterating each digit in their corresponding cells, and the cells are created by dividing the transformed image by the Sudoku size.
And then here I can take over by talking about some of the image filtering and AI model flowchart. So essentially, we start with the AI image, we start with the Sudoku image. We apply the various filters needed to filter the image, such as the hue lines transform, Gaussian filters, dilation filters. And this is all to just remove the grid lines and get each sub-image of the Sudoku image so that we end up with 81 total images, one for each digit of the puzzle, or a blank square if there is no digit in that square. So then after we do that, we iterate in a for loop 81 times because the Sudoku board is a 9x9 grid. And for each of those 81 times, we pass the digit to the digit recognizer model and we get the outputted digit. And then again, we store all these values in the 9x9 matrix. So just a few terms to go over. Gaussian median filters, those were used to smooth or sharpen the image. Threshold was used to convert the image to binary in a few cases. Gainy was used to find the boundaries. Hue line transform located the horizontal and vertical lines for us to remove said lines. The contour detection was actually used to find the outer edge of the image in order to center it properly and crop out the rest. And so was the perspective transform, which allowed us to orient the image in such a way that's a perfect square, so we could actually perform our other filters. And then about the AI model, this AI digit recognizer model is from GitHub user Nikon, is actually the AI model that I believe Dr. Mirza used a couple times in his lectures for reference. And we were able to find the guy's GitHub, and this is a demo of basically how it works on his end. His application used a front end HTML web server, which we made a couple of changes to how it exactly worked, but we kept the model intact for use in our code. And so his model, just a little bit more about it. So it used the MNIST dataset. It has 2 CNN layers, batch normalization, atom optimizer, and it sends the input digits for better recognition. It has 99.3% accuracy. So in order to actually utilize the code, a few adjustments were made specifically to the inputs and outputs, and then that way we could actually just pass our images into the model and then save the outputted number instead of writing it on a locally hosted web server like that. So that was removed, and we just integrated the rest of the Python in the application.
Now, if you look here, I can explain how the Sudoku solving algorithm works. Essentially, the algorithm is going to obtain input from the digit recognizer. The digit recognizer is going to output a double list. And from there, the input for this Sudoku algorithm is going to look like a traditional Sudoku puzzle. But instead of just empty boxes there, the empty boxes will be zeros. So from there, the algorithm is going to be looking for all of these zeros, seeing, can I place a number here? Can I place it in this row, column, or box? And it'll check if it's even legal to assign a number to that specific location. So essentially, the algorithm is solving the Sudoku puzzle like an average person would, except instead of solving the puzzle in 10 minutes, the algorithm will solve it in less than a second, essentially by backtracking. Pretty much, the algorithm will keep checking this number, any number from 1 through 9, and see if that assignment is legal. And if it is, we're going to keep the number there. And if not, we're just going to keep going back until we can find a number that will fit as per Sudoku's rules. And then from there, once it is done assigning a number to all of those locations, it will print the solved Sudoku grid again as a double list or a 9x9 matrix. Was I muted? Oh, I'm sorry.
Here's how we overlay our calculated solutions. The solution is inputted using a double array with the red numbers from the digit recognizer being zeros. As you recall from earlier, we mentioned like filters. One of those is like the mask as well as the contours that allows us to crop the Sudoku puzzle by getting rid of the background and as well as transforming it to be able to be a flat 2D picture that then we can process. So how we did it is by resizing the picture into a square, as well as using Opencv's .shape function to get the pixel value of the height and width of the image. Now that we have the size of the image, we can, how I did it is divide that by the Sudoku puzzle size to be able to get 81 cells. Now we can iterate through the cells and place each non-zero digit onto the corresponding cell on top of the original image. The size and position of the text are adjusted to be able to center it. And the dynamic overlay process, we have a feature that can detect horizontal and vertical lines that could count to determine the Sudoku size. So in the future, we could add features for 6x6 or 3x3 Sudoku puzzles. Here is our visualized picture of how our problem works. Here's a really realistic example of our program at work. As you can see from a newspaper, the contour detection and the morphing algorithm work as it was able to crop out the puzzle and transform it into a flat image. And our filtering algorithm cleans up the cell to recognize the digit. Here you can see our program outputs by next slide. Here you can see our program's output by stages. As you can see, that the digit recognizer outputs the read values and zeros for the empty cells, while the solver algorithm completes it by solving the puzzle and getting rid of the zeros. And for the overlay matrix, all we had to do was subtract the digital recognizer output by the solver algorithm to get the zeros to be able to overlay the image over here. As you can see, it's very clear. The borders are cropped out. The solution is centered. Next slide. And we ran into a couple issues during development. Lighting has been one of the biggest ones, as like everyone here would have probably encountered. We managed to get through around this when it comes to cropping out the image by almost every like angles and lighting, but the problem came when it comes to the digit recognizer, since our model was trained using handwriting. Sometimes it can't recognize printed text or has trouble, as well as if the filters could not clean up the border properly of each cell, sometimes it reads the borders as an extra one. And combining different outputs from each algorithm, from each process was also a difficult task because each model can use like a different output. So we managed to modify those. Next slide. Here are some improvements that if given more time, we can improve our filterization to get the puzzle from lighting and orientations by adjusting our threshold. We did do adapted threshold for this, but it needs more adjusting to it. And we could attach a camera for real-time overlay for the solution. So a person will be able to move the puzzle and it would keep the solution on top of the paper. And we would like to create a GUI. And our plan was also to create, modify a 3D printer to draw and solve the Sudoku puzzle. And here's our closing remarks.
And then just some closing remarks here. So basically, we created a Sudoku puzzle solver using a combination of Opencv and AI. Most struggles actually came from the image recognition themselves. Many improvements could be made. I mean, next time we would also probably train a model for this as opposed to using a pre-existing one, although the pre-existing one did work pretty well. And I think overall, we learned a lot about designing machine vision application. And then here's some of the references, one of which is said digit recognizer.
Thank you, Group 8. Great project, fun project. Good job.
Thank you.
But you took the fun out of solving Sudoku. Anyway, we're going to open up for questions here. Any questions for the group? Make sure to unmute mic if you are asking a question. You can unshare your screen also. So I do have a question while others are thinking. Why did you use AI for recognizing digits versus built-in OCR functions in Opencv?
Well, that's a good question. We actually originally also wanted to incorporate, and we were able to test this to some degree, but it definitely is a work in progress. If someone were to start solving the Sudoku puzzle and they got like stuck at a point, we could help them solve the rest of it. We could just give them the solution.
That's a great answer. I was going to ask that. Can it give a hint if you're stuck on a Sudoku puzzle? That
we were able to test it. Yeah. There was one example where we were able to test it with. It might have then been with this puzzle too. Where I think I filled in a 1 and a 7, and it recognized those digits and it was able to solve the rest of the puzzle as well.
And you used a brute force method to solve it, right? Like trying out
Yes.
different. Okay. Well, it works. If you have computing power, you can do that. More questions for this group?
I'll throw one out there. This might be pretty hard, but I was just wondering, are there other applications that this could be used for in the real world?
Yeah, that's a good question. I feel like definitely yes. I guess it would depend on the application exactly, but like OpenCV in general can be used to do a lot, can filter images, and then AI, especially digit recognition. I mean, the MNIST data set is specifically meant to train, like, is a data set for handwritten digits. So people can make their own digit recognizers as well. So there's a lot of different applications there of just recognizing numbers on a thing. You could make like, I mean, just spitballing you could make like a license plate recognizer or something. You know, you could get the digits of people's license plates, like if you're a police officer, or you could yeah, I don't know, like maybe find someone's address on a house if you're looking for an address, and you know, like there's so many different applications you can do with just recognizing numbers in the real world, I think.
All
Thanks.
right. Any last questions for this group?
Good job. Thanks.
All right. Good job, group number 8. That was a good demo also. We're gonna move on to group 9, which is showing bowling assistant. Take it away.
Hello, everyone. We're Group 9, and as Professor Mirza said, we're doing the bowling assistant. I'm Stefan Maiorano.
I'm Nick Spanos.
And I'm Thomas DeSchutter.
And before we get started, we're going to show off our demo video. All right, so the main idea behind this project was throughout the year, we've seen a lot of machine vision applications for industry, assembly lines, food processing, all that stuff. But as things like this become more developed, you know, you can come up with ideas for personal use. And a lot of these, like we already saw with the, you know, Sudoku solver, are guiding people in learning or playing various games. And as you can also see, I got a lot better at bowling from all this. So next slide. So, like I said, our main goal was assistance with people who are bowling, learning to bowl, or just need a little bit of help while they're bowling. And we wanted three main functions, which was showing the remaining pins, highlighting them, drawing a contour around them on the screen, pointing out where to throw the bowling ball by tracking those remaining pins and deciding where to draw an arrow based on where the most of them are massed or congregated, and also displaying the score on the screen to know how many points you've earned from knocking down pins. And then next slide. So the main software we chose was Opencv, also Python, of course, and running it through Jupyter Notebook. And there was the question of if we should use MATLAB with it, but Opencv is the widely used vision application software. Same with Python in general. And there were a lot of libraries, functions, and examples we could draw from. We used a lot of those filters for this project, Hoff transforms, things like that, and it made it a lot easier. And then next, I'll hand it over to Nick to discuss the software flowchart and functions in more detail.
Yep, thanks, Stefano. So when we first start our program, of course, we initialize our system and import our libraries. The three main libraries that we're using, of course, one would be Opencv, and we use NumPy, and then also Matplotlib. Then we enter our video loop. So as you guys saw in the demo video, this is all happening in real time. So what happens is we enter the video loop, then we go and move on to image capturing. Once each frame's captured, we kind of pre-process that image. So we will grayscale the image, and then we also apply a small Gaussian filter over it. And then we send that through Huff circles, which is what is using no, sorry, Thomas, previous slide. No, you're good. We're still using that to kind of draw the contours around the pins. And then this is also what is kind of detecting the pins. We put that information into a matrix. And then the next question is how many pins are left standing. So basically, was there a strike or not? If there was not a strike, we'll highlight the remaining pins, draw the arrow, and then kind of put the score on the screen. If there was a strike, we'll display strike on the screen and then write the score. And of course, there'd be no pins highlighted, so nothing would be drawn. And then this can go on basically until the user is done playing. On the next slide, please, Thomas. And then here, as you guys kind of saw in the video on the right, we have our final setup. So this consists of a small bowling lane with a camera mounted on top of a tripod on a table. This was done to get the best kind of field of view for the pins, because again, Huff circles, we're trying to detect circles, so we want the camera directly above the pins. And then that position also helped kind of reduce noise from the lighting sources. So if you guys can tell on the right, sorry, I misspoke, on the left image, which was one of our early setups, you can kind of see at the top some brighter circles. Once we were able to move the lane, we were able to eliminate one of those and then kind of filter out the other ones. And then, as I had said previously, we still are doing this all in a live feed. And then, yes, this slide that Thomas just went to, we're, as I had said earlier, using Huff circles to detect the pins. And the great thing about that is that we were originally going to be doing kind of contour detection and then drawing contours on those pins, similar to one of our homeworks. But we had realized that we would have to kind of crop the image and specify an area of interest. And that still didn't fully get rid of some of the other contours. So we didn't want that. And so we found this function, which allows us to adjust basically the min radius of the circle, the max radius of the circles, and then also the radius between the circles, which really helped us reduce false positives in our program. and eventually allowed us to just display everything on a live feed. And now Thomas is going to go through kind of our results.
Okay, so for pointing to the pins, as Nick mentioned, we got the information from the Hoff circles and it creates an array. We wanted to separate the X values and the Y values for each circle into separate arrays. So then we could then calculate the median value for all of our remaining pins. And then basically to draw the arrow, there's a function in Opencv, which basically just draws a line. You choose a start point and an end point with the X and Y coordinates. For the endpoint, obviously it would be that median value. And the start point, we basically just had it at the center of the lane. And then moving on to keeping score. So as we loop through the circles array, we increment a count. So count the number of pins remaining at any given time. And then we can easily calculate the score based on this value given from just subtracting it from 10. And then we display that score on the video game frame. Again, it continuously updates, as you can see in the picture on the right. And then just a conclusion / summary. It worked as desired for the most part for what we were trying to do. Some potential improvements that we noticed is that sometimes it would detect other objects such as someone's foot or weird lighting on the floor. When we initially started doing it, we were more focused on just the part of the lane that had the pins, so we didn't really think about this. But then when we went to the full view, we noticed that was happening. In addition, we'd also like to create a full game where we update the score continuously. Probably do this by implementing a button press to update, basically grab the score from the current throw, and then it would update on the screen. And then also refine the arrow placement. So maybe have a way to detect where the person's hand is. And from there, we would draw the arrow to the point of the most pins. And that's basically concludes our project. Is there any questions?
Thank you, group number 9. Good job. Okay, so that was a good sports project. You guys took the fun out of bowling now. Made it automated. We're going to open up for questions here from anyone. And you can also unshare the screen, guys. Okay, one small comment I'll make is that this was a great application if you had also combined projected AR on top of the board showing the arrow. I'm not saying you should have done it, you didn't have time to do it, but if you actually show it where you're playing, the direction where to hit it, that would have really made this a very, very fun project there. Okay. Questions? Okay, as others are thinking, I'll ask this, that you guys use the Hoff circles to detect the pins. Did you actually use that over the entire image to detect the wherever you found circles? Or did you actually first detect the bowling setup, the board itself, and limited your search in that board?
So we did want to go the route of kind of cropping the image down and only, I guess, detecting those circles on the lane. We would have probably done that if we had more time, but like what we've shown here is we've just done it on the entire image.
Okay, and that's where you saw some of those issues where it was detecting circles at different places.
Yeah.
If you had gone the route of detecting the board first, how would you go about doing that?
So we did discuss this. We were thinking we would be drawing a contour around the entire lane and then a bounding box and then cropping the live feed to that bounding box. And then once we did that, we would kind of take that image and then feed it through our filtering process.
It would be a manually drawn bounding box?
No, we would have been doing it like kind of like adaptively, I guess. So anywhere in the frame. We just hadn't figured that specific thing out yet, but we did have like ideas on how to do that.
Okay.
And also with filtering and everything we did, and changing the parameters of half circles. There weren't actually any circles detected on the lane. It was just really the tip of a shoe was close enough to a circle for it to detect. But luckily the bowler isn't in frame, so it didn't mess things up too much.
Right. I mean, whenever you're using algorithms like that, line detection, circle detection, it's going to try to do that all over the image, and it will pop up where you don't expect it either. One more question I had was that when you actually drew the arrow for where to hit, how did you determine the starting point of the arrow if you didn't have the bowling board set up not in the image itself? How did you locate the starting point of arrow?
So basically, we just basically found the center point of where our setup was because we marked where we had the camera and the bowling lane with tape. So then whenever we would set it up, it would always be the same. So we basically just found where like the middle of the lane was, and we had that as our starting point.
Okay, so it was a tuck point.
Yeah.
Okay. So if you had the board detected, then you would know where the bowler is going to throw the ball from.
Yeah, exactly.
Okay.
I have a question to add on to that. Did it matter? Like, did you think about perspectives of left-handed versus right-handed bowlers when determining that point?
We did not, unfortunately. If we had gone the route of actually using the person's hand or something to decide where to throw the ball, we probably would have considered that.
And also, if you have to spin the ball also, right?
Yeah, that's
Straight
true.
line. It can make it as complex as you want. Yeah.
Mhm.
But good job doing it and implementing a working application. So that's the goal, that you use the things you learn in the class and actually use half circles there to do a useful application. All right. Good job, guys. All right. We're going to move on to group number 10. And they are going to show golf swing mastery. Take it away.
All right, good morning, everyone. We are Group 10 presenting our Golf Swing Mastery Machine Vision project. My name is Ethan Talampis, and my group members are Saeed Anas and Cynthia Yang.
Golf Swing Mastery by Group 10. Here we have Saeed demoing our program for posture for a golf swing. As you can see, when you are standing too straight, the neural net turns red, notifying bad posture. When in the correct form, it turns blue, showing good posture. And when you're leaning too forward, it turns red again. Now we have the view facing the golfer, which monitors the arm and shoulder angles. For the arm angle, Saeed's left arm should stay straight during the backswing. As you can see, when he bends it, the neural net turns red. In this clip, Saeed manages to keep his left arm straight, which notifies him that his arm positioning is good. This point of view also monitors shoulder angles. Saeed's shoulders should be perfectly even. As you can see here, when one shoulder becomes higher than the other, the neural net becomes red. Next, we showcase how the program works all together for this point of view. First, we have Saeed demonstrate what it would look like for a bad form swing. And next, we have Saeed demonstrate what a perfect swing would look like. This concludes our video. Thank you everyone for watching.
Okay. Now to introduce our project, golf can be a pretty tricky sport to get into, especially since there are many intricate body mechanics to the swing. And the three things that this program tracks were what I personally struggled with when I started golfing. So that was sort of the influence on this project idea. And utilizing what we learned about in this class, about Opencv and neural nets, we can help beginner golfers learn more about their swing. So MediaPipe was a neural net that we decided to go with for this project. And a little bit about this program is it's a framework developed by Google, and its neural network capabilities offer real-time precision, providing immediate and accurate feedback for refining techniques. And this technology enhances our training experience, ensuring comprehensive analysis and improvement to one's golf swing. So the way that we designed this project, we set up 2 point of views to monitor the golfer's form. The first angle is either behind or in front of the golfer, and this will mainly monitor whether the golfer's posture is good or bad. And this will give real-time feedback indicating correct or wrong posture based on the golfer's hip angle. And then the second point of view is facing the golfer, and this will track the shoulder positioning and whether their guide arm stays straight during the backswing. And now I'll hand it off to Cynthia to discuss more about how our program works.
So here we have the flow chart. The first thing to consider was which angle we wanted. So the posture, we wanted to do the hips, the elbows, and the shoulders. And based on that, we decided where to put our cameras. So with that, we use the algorithm from pose detection with MediaPipe. And there we got landmarks mapping our hips, elbows, and shoulders. And then you can see it branched off into our 2 camera views, the side view and the front view. The side view captures the angle of your hips to see how much leaned forward you are or how straight up you are. And the front view takes the angle of your elbow and your shoulders to see if your shoulders are even and if the elbow is straight. And then for our outputs, we made it so then the outline of your body would be red if it was a bad posture, blue if it was good. And we also had a little text box in the upper corner to tell you if it was good or bad for the elbows, hips, and shoulders. Here's a little snippet of our code. This is for the back posture of the hips. You can see for our landmarks, we got landmarks from the shoulders, hips, and knees, and we calculated the angle for it. And then in the second one down below, we put parameters up to tell you if you were in the right position. If you were too leaned forward, it would be bad. Too straight up, be good. So we decided that between the angles of 155 and 170 was a good posture to have for your hips and back. And then so for the shoulders and arm form, we got landmarks from both shoulders, the elbow, wrist, and nose. To calculate the angle for the elbow, we use the shoulder, elbow, and wrist. And then for the shoulders, we actually used the nose to consider how far your nose was from your shoulders. So when the shoulders were uneven, the shoulder will be closer to the nose, and that's how we considered your shoulders not being straight. So for in the code in the bottom, the angle for your elbow was going to be greater than 165. And for the shoulders, they had to be 0.04, the difference between them from the nose to make it straight. And then so here are more of our results. You can see in the top two pictures, those are our side view angles. Reading the hips. In the first one, he was too straight up and it gave a output saying bad along with the red outline of the body. The next one was a good posture, outlines blue, and the hips say good on top. And on the bottom, it's reading the elbow and shoulders. The shoulders were off. One was higher than the other in the bottom left-hand picture. And the elbow is bent. And in the very last picture, the bottom right hand, good posture and good shoulders and good elbow.
All right, so throughout the entirety of the project, we did face a couple of challenges. One of the major challenges was actually starting the project itself. So at first, for pose detection, we decided to use Opencv, which is another pose detection software, but we had a lot of issues getting this to work consistently and getting it to run in the first place. So from then we discovered MediaPipe, and MediaPipe had a lot of good advantages like having Google TensorFlow and stuff built in for further development. And we also developed issues with it reading the landmarks of each body part properly, depending on what you're wearing. So lighting wasn't a big issue with posture detection. For what we tried, like in our video, was really dark. But if you're wearing like a jacket, when we tried it, it would like completely misinterpret like your arm. So if your arm was down, it would say it was in the air. So we had to fix that by wearing short sleeves. And if you're wearing like a thicker jacket, it wouldn't detect the change in elevation with your shoulders as well. Even though you can visually see it, the Opencv software, the MediaPipe software wouldn't show it. So going on to the next slide, we have possible improvements we could do. One would be using Google TensorFlow to add machine learning as they can be used in conjunction with MediaPipe. That way we can add more forms of posture detection as there's different golf postures that can be learned and analyzed, as well as it would make easier to add features such as the wrist form, as well as the form and position of your golf club. So those can all be added through machine learning and model detection. Another thing we wanted to implement is multiple cameras. So instead of doing the front camera and side camera separately, we could run them together at the same time. Opencv does allow for this, but we did have some issues getting that to run. So we just decided to do it separately for now. And in conclusion, we found that what we got was very useful for learning how to golf. It shows that machine vision has lots of applications. In the video, you can see that I was like learning how to do a golf swing, and it helped me learn because I never swung a golf club before, and I did learn that specific posture a lot better. And that also shows how it can be expanded to other sports and other things where posture is really important, even in the medical field where posture is very important in standing up correctly. It just shows how expandable it is and how easy it would be for someone to implement. And overall, our project was a success, and I thought it was pretty cool that I got to learn golf at the end. Any questions?
Good job, Group 10. All right. I think it was another great use of MediaPipe for a real application, and you guys showed that you can design applications like that. So that was excellent. We are open for questions. Anybody has a question for Group 10?
Question as someone who's trying to learn to golf. Can I use it outside on the golf course, or does the background matter so it won't work outside?
That's a great question. So I'm sure that it'll probably be even better outside, especially since, well, lighting wasn't really a factor, but natural lighting will definitely be more useful to help you understand your pose. And so, yeah, I think definitely would work a lot better outside on the golf course.
Okay, cool. Thanks. Good job.
And that's a hint so that you can make it a real application, Group 10. More questions? Go ahead.
There, in the presentation, you talked about there was a range of angles where you determined if it was good posture or bad posture. So what was the process you went through to determine what that range should be?
Excellent question. I had the same question in mind.
Well,
Honestly, I'm not a golfer myself either, so we went off of Ethan and we would ask him constantly throughout the entire experiment, like, do you think this is too much of an angle? He's like, and he will like give us feedback saying, yeah, that's too much of an angle. We need to make sure they're not too leaned forward or too leaned back. So I guess we based it off of his experience.
Okay, so if you had a real golfer, it could help you tailor the ranges. So I think, yeah, that's an important question that in order for it to be a real application, you have to have data which really makes sense. Now, would it be different for different people, or the angle coming from the media pipe that would work for any person, any size person, because you're looking at the angle between the joints, right? So what do you guys think about that?
We didn't have much trouble doing it between all three of us. It read us perfectly fine. The only problem we really had was when I was wearing my big sweater and it couldn't really get a good reading on my arms. But other than us three, we didn't really try it on anyone else.
So personally, I do think it might be a bit of an issue with different body types, because I know different people have like different hip widths and different, body types and architectures. Some people have wider hips, some people have narrower shoulders. So I think since we're using those as landmarks, it might detect it a bit differently. But I think that would require further development if we really wanted it to be accurate with like Google TensorFlow. It would allow you to upload sample postures from like many different body types and use that in conjunction for better flow. But I think since golfing posture doesn't have to be extremely precise, it worked pretty well for when we tried it between the three of us.
Okay. Any other questions for this group? I thought the way you detected the shoulder angle using the nose as a guideline, what is closer to the edge of the shoulder, was a nice way to detect the posture, shoulder posture. So yeah, there's a neat ways you could do, and once you have the body as a wireframe to detect all those different qualities of your posture. Any last questions for the group? All right, good
Just have a
job,
quick question.
guys.
Yeah, Dr. Mirza.
Go
Yeah,
ahead,
so,
Dr.
so
Ming.
yeah, when the team mentioned about using TensorFlow for the Google stuff, have you guys actually just made a rough estimation how much data you may need in order to improve, for example, some of the precision?
I'd love to answer that question. So I actually did, before we tackled the method we showed and how we accomplished the program, I actually did initially try using Google TensorFlow to train the golf model. And I think you can do as little as probably 5 or 10 sample images. So you upload your sample images and then you train it based on parameters you can give it and sensitivities, because our original program is just detecting shoulder, hip, and elbows. But I think with the way TensorFlow is incorporated in MediaPipe, we could easily add our postures between the three of us, so like 30 images, as well as ones from internet or ones we find like people showing what a good posture look like in like a spreadsheet. You can upload as many as you want, and the more you add, the more better and more accurate I think it would be. But to answer your question, we could probably do as little as 10 showing what a good and a bad posture looks like, because it looked like TensorFlow and working with MediaPipe is very accurate and efficient.
I'm glad you had the experience before. It looks like you had the experience with TensorFlow, right? Before. Yeah. Okay. Yeah, I was just curious about some of the precision improvement you may have, but I think you're heading in the right direction. Thank you. Thank you. Thanks.
Yeah. Thank you, Dr. Ming. One thing I would note that, I mean, a golf swing is about the motion also. So can TensorFlow handle that, or you have to kind of subdivide your swing into different areas where you're monitoring the posture all the way through? With the media flow, your angle has to be within certain range, so it can continuously monitor it. So I think a mix of both could be really nice here. So you guys are on the right track here. Make a very practical, useful application, and you tried out various stuff. So good job on that. Good job, Group 10.
Thank you.
All right, we're gonna move to our last presentation. Group 11, Blackjack Helper. Oh, going to Vegas now. Take it away.
Okay, so this is our Blackjack helper. I'm Julian Haddad.
Badawi.
And then here is our demo video.
So here is another program we wanted to implement, but couldn't because of time constraints. So pretty much this one here doesn't use a webcam or anything, but simulates a real life blackjack game where it has a player's hand, dealer's hand, the sum total of both, and then a card counting feature. So we wanted to implement this with our webcam based program, but we weren't able to due to time. But with this one, pretty much player here has a 13 against a 10, so they would hit. So the player would just type in hit. And the player actually ended up busting. So here you can see the card count went to -1. And then if a player wants to play again, they would just type in yes. And here player has a 20 against an 8, so they would stand. And then it ended up beating the dealer. And then if they want to play again, they can. And if not, player would just type no, and the game ends there.
So Blackjack is one of the most popular games actually played in the casino. It does involve a lot of high skill or high luck, but with basic strategy, and you'll be able to greatly increase your odds. So our goal was to help a player, whether they've been playing for years or just recently picked up Blackjack. It's a very friendly user interface that allows the player just to be able to pick it up and be able to learn from it. So we wanted to use machine vision to basically be able to correctly detect each card, give it a value, and then we also allowed it to display the suit. And then we wanted the program to be able to make optimal decisions between hitting or standing. And then from there, we wanted to give a technological advantage to players, improving their chances against the dealer.
So for the user interface, what our initial plan was to have the camera go live and be able to detect the cards and that start in play and send back the signal back to the player and be able to have a counting system so that it'll be able to help the player to decide what his next play will be. Go next, please. So for our method, we just wanted to use the live webcam detection and be able to analyze and detect the cards that are in play and give some information about the game and so that the player can uh, be able to know what his next move will be. You go next slide. So more about the technical details is we were using Opencv to create the code. How the live camera works is that we implement the code to use different filters such as the grayscale image, canning detections, and canny edge detection so they can find the contours of the cards in the live video. And once it's able to detect the cards in the live video, it will go back into the code and compare the different images that we stored in the code. And for the other code, we just for the game we set two different classes such as the ranks and the ranks and the suits. We're able to tell which cards is which and then play the game. And then we also have a counting systems where if the cards are around 2 to 6, it will be considered a +1. From 7 to 9, it will be considered a 0 count. And from 10 to 8, it will be considered of a -1. So in the game, depending on these situations, um, it will be able to give a probability of what's the next card will be. Next slide.
I would be going over the results. Here are results on screen. You can see the card is being recognized in real time, displaying each card's value and suit on the top left of the card in green. This can only happen in best conditions. What I mean best conditions is that the cards need to be laid out in a dark background with little to no glare. This causes the cards to be read in the most accurate way. On the bottom, you can see our card counting game that Cha was talking about. The longer the game goes on, the more cards are dealt, which in return gives a better reading of what card might be next, either a high or low card. How card counting works is that the low cards increase the card count because they increase the percentage of high cards left in the deck, while high cards decrease the count for the opposite reason. Think of the higher the card count number, the higher the chance of the next card being dealt will be a high card. If a card count is 0, it means it can either go either way. So you have like a 50-50 chance. As you can see on the second example on the left, the players dealt an ace of diamonds and a 9 of spades. This equals 20. And the dealer is showing an 8 of spades and the other card is hidden. These are pretty high cards that are dealt. So the card count is -1, meaning if the player decides to hit, they are more likely to get a lower card because of how many high cards were already dealt. Next slide. Challenges we faced. We faced multiple challenges during this project. One being when we used images from online, we encountered image sizing, image resolution issues that either caused the cards to be read inaccurately or at times not be read at all. So we decided to use our own images. So Cha took the deck of cards we were using and he took 52 high quality images of one of every single card. This fixed the issues that we had previously, but we were still at times getting inaccurate readings for some of the cards. So we decided to crop out the images and that made a huge difference. Another challenge we faced was detecting cards live at first. So we thought about abandoning the live view idea and just capturing an image and having it compare it to the templates like that. But we thought that wouldn't be as practical in a real life environment. Also, we faced some problems with thresholding either being too high or too low, which caused cards to not be read at all or having it read as 2 cards. Next slide. Future improvements. Some future improvements we could make was to first, we could train the model with thousands of pictures with different decks of cards as well as different backgrounds with also high quality and lower quality pictures so that it could detect the cards at any conditions. We also wanted to integrate both card detection and the card counting simultaneously, but due to timing issues, we were unable to. Going off that, we could also have it so that a percentage probability would show the player what probability of getting a certain cards would be. Another would be the ability to split cards. Also having it so it could detect a whole playing table with multiple players, not just one player. And also a big one would be to be able to count cards with more than one deck, since in the real life they use about 3 or more decks. And also having a feature where bet sizes or chip sizes values are detected and shown under each player's hand.
So in conclusion, just take into account the importance of basic strategy. Our program is there to help players improve, but that doesn't mean that you're just going to win 100% of the time. Obviously, gamble responsibly and only be willing to lose a certain amount, and don't obviously gamble everything away.
All right, good job, Group 11, and ending with a public service announcement there. Well, I want to know if this is legal in Vegas. You're doing card counting.
It's legal if you don't know, I guess.
It's for entertainment only. Okay, let's
Yeah.
open up for questions. Well, you guys had a good use of filters that you learned in the class to develop this application. So yeah, well done there. All right, let's open up for questions for our last group. Anyone has a question?
I guess I have a question. Since you guys are doing contours, right? Did you guys implement like a max and minimum area for the contour to be able to detect it kind of like better, since you guys know like kind of the size of the cards?
Yeah, so we determine like the size of the card and be able to try to find the max and min of the best way to find the contours of the image in the video.
All right, does that answer your question, Emmanuel?
Yeah.
All right, more questions? So you guys did template matching, right? For detecting the card, the different
Yeah.
types of card. So
So originally go ahead.
Go ahead.
Originally, we found something just online, a folder of like, I think it was just 52 images of each card. That didn't work with what the cards we used. So Cha actually ended up taking pictures of his own cards. And even through that, there was like a slight background in it and it still wasn't detecting. We had to go back and then crop every picture just to show the edges of the cards only. And then through that, then we were able to just match it with our own images.
Okay, so I guess there are two things going on. First, you have to separate the card from the background using certain algorithms and filters so you can reliably see where the card is, and then in the card do a template matching.
Pretty much.
Now with the template matching, it's going to work for only that set of cards, right? If the images are slightly different, for example, the high cards, the Jack, Queen, King, they look different in different set of cards. Would it recognize it then, or would it have problems?
No, it wouldn't. It just recognized our own. So if we wanted to, we would just have to add in, thousands of more pictures of whatever amount of cards, then it would be able to detect anything.
Or you could use a machine learning approach.
Or yeah,
So
the
you could,
easier way, yeah.
yeah, that's another way to do it, because if your data is quite variable, then that type of approach works well. More questions for this group? All right, so that was a good job, guys. You accomplished your blackjack player there. I mean, if you add Chat GPT with it, you have an AI player which can play in Vegas now. Anyway, all right, so guys, thank you very much, everyone. That was great session, great projects. I really enjoyed all the 11 projects. I will be posting videos on YouTube. Laura is here. I hope she's still here. She's going to help me post it on LinkedIn also. You want to say a few words about that, Laura, once you get those links?
Sure. So what we'll do is in our SECS Career and Life Design group, we will post your video links, and I can send the information so that you guys can join the group, so then I can tag you and people might watch them and ask questions or comment on it. It's a really good opportunity. We have a lot of employers and alumni in the group. So as soon as Dr. Mirza sends it to me, I will send the email to you guys so you can join and I can tag you.
So no pressure on me here. I have to upload all your demo videos to the YouTube, and then I'll send Laura those links. And guys, those demo videos, I know sometimes through Zoom, they don't come out very well or smooth or loud, but when you see them on LinkedIn, on YouTube, they will be as you submitted with the project. So you will see it in full glory there. And
Dr.
also,
Mirza does a nice job of putting it together for you guys. So he gives me all the information that I need, which is amazing. All you guys need to do is join the group, and he does everything else for you. So
thank you, Laura. And make sure that you guys have a LinkedIn presence, okay? Because when Laura posts these LinkedIn group news feeds, she tags your name. So if anybody say, hey, these 3 group members, I want to reach out to them, somebody from the industry, if you have a LinkedIn presence, they will directly go to your personal page and can reach out to you. So that's a really good use of tool to advertise what you did to everyone, okay? Any last comments from our guests about the presentation for our students? Any tips or anything? Please feel free to share at this point before we sign off.
This is a great class, Dr. Mirza, and thank you for the organization and your dedication to the success of our students and this projects. Thanks, Laura, and everybody. It's truly a great session. Thank you so much.
Thank you, Dr. Ming. And it's really the students who went above and beyond what they learned in class to really try out and make successful projects. I feel so satisfied when I see all this, that they learned what they saw in class and practical applications. So kudos to everyone. Any other comments? Go ahead.
Just congratulations to everybody. Well done, and should be really proud of yourselves.
I second that, Deborah. Okay, so with that, thank you, everybody. And now prepare well for finals for next week. And we will see you on Tuesday for final early. Take care, everybody. Have a great day.
Thank you. Take care.